Hello again. This is Math 2115 coming to you from the College Edu page, and this is the conclusion of the lecture entitled Computer Science Connections 1. As always, be an active learner while watching this video. When last we met, we had the system specification that was given here, and I asked you to solve this. If you solved it, congratulations. If you didn't have time to work on it, I'll give you an opportunity to work on it now. You know what to do. Let's see how you did. Okay, the three specifications were from the earlier example were true only in the case when P was false and Q was true. But this new specification using the same designations is negation Q, which is false when Q is true. Consequently, these four specifications are not consistent, or we would say inconsistent. Again, an easier way to do this is with the truth table. In the same way, in the previous example, we crossed out these first two rows, and we crossed out the last row, and these were the system specifications, but you see that these are true and this is false, and that means they were inconsistent. So now I'll talk about another application called Boolean searches. Logical connectives are used extensively in searches of large collections of information, such as indices of web pages. Because these searches employ techniques from propositional logic, they're called Boolean searches. In Boolean searches, the connective AND is used to match records that contain both the two search terms, or is used to match one or both of the search terms, and the connective NOT, sometimes written as AND NOT, is used to exclude a particular search item. Careful planning of how logical connectives are used is often required when Boolean searches are used to locate information of potential interest. So let's look at some examples. Most web search engines support these searching techniques, and that can help us find web pages about subjects. So for example, here we're going to want to find web pages about universities in New Mexico. We can look for pages matching New and Mexico and universities. The results of this search will include those pages that contain these three words: New Mexico and universities. This will include all of the pages of interest together with others that we really don't want, such as a page about new universities in Mexico. Note that in Google and many other search engines, the word "and" is not needed. It is understood because all search items are included by default. These search engines also support the use of question marks that search for specific phrases. So a more effective way to do this would be New Mexico in quotes and universities. Next, to find pages that deal with universities in New Mexico or Arizona, a different example, we can search for pages matching New and Mexico or Arizona in parentheses, because I do that first. And then I do and universities. The and takes precedence over the or operator. Also in Google, the terms used for this search would be New Mexico or Arizona. The results of this search will include all pages that include the word universities and either both the words New in Mexico or the words Arizona. Again, pages besides those of interest will be listed. Finally, to find web pages that deal with universities in Mexico, not New Mexico, we might look for pages matching Mexico and universities. But because the results of this search will include information about university in New Mexico as well as university in Mexico, it might be better to search for pages matching Mexico and universities together in parentheses, not new. The results will include pages that have both the words Mexico and universities but do not contain new. And not is the way you sometimes get replaced. You don't type it. Sometimes you just use the word minus. In Google, the terms used for this last search would be Mexico universities and minus new. These concepts with logic are also used in logic puzzles. So puzzles that can be solved using logical reasoning are known as logic puzzles. Solving logic puzzles is an excellent way to practice working with our rules of logic. Also, computer programs designed to carry out logical reasoning are often use well-known logic puzzles to illustrate their capabilities, and sometimes these are called test vectors. Many people enjoy solving these puzzles, and sometimes this is called a part of recreational math. Now we're going to discuss two logic puzzles here, and the first one is a puzzle which deals with an island that has two kinds of inhabitants. That means everybody there is one class or the other class. Knights, who always tell the truth, and their opposite, knaves, who always lie. Sometimes versions of this talk about liars and truth tellers. But anyway, that's what we have. You encounter two people, A and B, who are inhabitants of the island. What are A and B if A says B is a knight and B says the two of us are of opposite types? Okay, you know what to do. And I encourage you to think about this and invest some time. Let's see how you did. Well, we start by providing some structures. So P and Q are the statements that A is a knight and B is a knight, respectively. So that not P and not Q are statements that A is a knave and B is a knave, respectively. So we do this by cases, which is a good way to approach a problem like this. We first consider the possibility that A is a knight. This is the statement that P is true. If A is a knight, then he is telling the truth when he says that B is a knight, so that Q is true. And A and B are the same type. However, if B is a knight, then B's statement that A and B are of opposite types, that would be represented by this. You see, it's either one or the other of these are true, and so this is the statement that that they're of opposite types. This is true. So either this one is true or this one is true. Would have to be true, which it is not, because A and B are both knights. So since A and B are both knights, both of these would have false truth values. Consequently, it's a contradiction. We conclude that A is not a knight, and then P is false. Now, if A is a knave, which we've figured out that he is, then everything a knave says is false. So A's statement that B is a knight, that is, Q is true, is a lie. So if Q is true is a lie, that means that Q is false and that B is also a knave. Further, if B is a knave, then B's statement that A and B are of opposite types is a lie, which is consistent with both A and B being knaves. So we conclude from this analysis that both A and B are knaves. You really do want to think through this kind of problem. It builds your strength in this area. Here's another logic puzzle. Father tells his two children, a boy and a girl, to play in the backyard without getting dirty. However, while playing, both children get mud on their foreheads. When the children stop playing, the father says, "At least one of you has a muddy forehead," and then asks the children to answer yes or no to the question, "Do you know whether you have a muddy forehead?" The father asks this question twice. What will the children answer each time this question is asked, assuming that a child can see whether his or her sibling has a muddy forehead, but cannot see his or her own forehead? Assume that both children are honest and that the children answer each question simultaneously. You know what to do. Let's see how you did. Well, let S be the statement that the son has a muddy forehead, and D be the statement that the daughter has a muddy forehead. And we know that they both have muddy foreheads. So when the father says, "At least one of you have this," he is stating that S or D is true. Both children will answer no the first time it's asked because they cannot see the mud. Each sees the mud on the other child's forehead, but they don't see their own. Therefore, the son knows that D is true, but doesn't know what's the case about whether S is true. And the daughter also knows that S is true, but doesn't know if D is true. So after the son has answered no to the first question, and the daughter also answers no, the daughter can determine that D must be true. This follows because when the first question was asked, if the son knows that S or D is true but cannot determine whether S is true, using that information, the daughter can conclude that D must be true. For if D were false, the son could have reasoned that because S or D is true, S must be true, and he would have answered yes to the first question. The son can reason in a similar way to determine that S must be true. It follows that both children answer yes the second time the question is asked, and answered no the first time the question is asked. Again, you want to think through this perhaps more than once. Not only are propositional logic used in software, search engines and such, it's also used in hardware. And this is first observed in 1938 by Claude Shannon in his MIT thesis. Claude Shannon became a legend at Bell Laboratories, where I worked, and he is known as the father of information theory. We may talk about him later in this course, but not here. So a logic circuit or digital circuit receives input signals P1, P2, all the way up to Pn, and each bit is either, each of the P's is either a 0 or a 1, off or on. And it produces output signals. The circuit produces output signals that are called S1, S2, Sn. And each of these is a bit of the output signal. In this section, we'll restrict our attention to logic circuits with a single output signal. In general, it can be more complicated and have multiple outputs. We'll talk about some of those later, in fact. So here are the symbolisms then. So this first one called an inverter. So it takes a signal 1 or 0 and it changes it to the opposite. And this little circle here is something that tells you it's an inverter and circuit. And also later we will talk about a NOR gate, not today, but later, and that will also have a little circle on it. Now this is called an OR gate. And here you get two signals, P and Q, being input here. Now the difference between an OR gate and an AND gate is just this curved surface right here, but this will give you P or Q. So depending on this, whether these are zeros and ones, it will output P or Q. That is known as an OR gate. And last, we have an AND gate. And again, the AND gate is different than the OR gate because this is a line perpendicular to the bottom of my chart, and it doesn't curve. So P and Q are inputs, and it outputs P and Q. And you can build a circuit that looks like this. You see there are parallel and serial elements, and the arrows indicate the flow of the current. And I think I really talked about everything. Okay, so the first question is going to ask you to figure out what is the input associated with this thing that's called figure 2 here. Now you can actually see that that's all written here nicely, and so just the way the question was posed, it's shown in blue here, and that would be the answer. But you see, I wouldn't have all those things. I'd have P, Q, and R, and the rest of this stuff I would not have, and I would be asked, so this is not this. These are here, over here. This is not here. This is not here. This is not here, and this is not here. You can see that, but you should think through and make sure you would know how to resolve that. So the way that I would probably ask a question like this is I would say P, Q, and R. I would show you them here, but I would not show you this. I would not show you this, and I would not show you this, nor would I show you this. And so you would have to use your knowledge of this logic circuit to come up with the thing I'm showing you over here. Now, more generally, what I would do is I say, given this equation of different inputs, so P, Q, and R, I give you all the possibilities as a truth table. What is the final output? And so you would have to, number one, figure out what this is and come up with this as an answer. So those are good problems for you to practice. So sometimes you're given a circuit and you have to find the input-output table. And other times you start with a schematic or a definition of the output, and you're supposed to build a circuit that will give you this as an output. And so you know what to do. Let's see how you did. Okay, so here is a circuit that will produce the desired outcome. And sometimes there are more than one circuit, and if I ever ask you a problem like this, I would have to check to see if your answer was correct. There is usually a best way or most efficient way to build a circuit, and good hardware designers want to do that. So anyway, this is an example of a second type problem that you could be asked. And now let's introduce LSA 3. So 5 women with different nationalities and with different jobs live in consecutive houses on a street. The houses are painted different colors. The women have different pets and have different favorite drinks. Determine who owns a zebra and whose favorite drink is mineral water, given these clues. The horse is in a house next to the diplomat. The fox is in a house next to that of a physician. The violinist favors orange juice. The Norwegian's house is next to the blue one. The owner of the greenhouse favors coffee. Milk is favored in the middle house. The diplomat lives in the yellow house. The photographer breeds snails. The greenhouse is immediately to the right of the white one. The Norwegian lives in the first house on the left. The Italian favors tea. The Japanese woman is a painter. The Spaniard owns a dog. And the English woman lives in the red house. More on this LSA in Blackboard. In closing, now more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now more than ever, take care of yourself and of each other. May God bless each and every one of you all.